Hello, everybody. Welcome back. I would like to introduce both of you to Terence Tsao and Preston Van Loon from Prysmatic Labs. They'll be talking about Ethereum 2.0 client infrastructure, block explorers, and a bunch of other stuff. So you can take it away, Terence.
Sweet. Let me share my screen. Share. And I'm supposed to turn off the audio as well, I think. How do I do that? Okay. Cool, thanks. All right, so let's get started. Thank you for having Preston and I here. And we kind of divide this into two sections. In my section, I do a little brief overview of Bitcoin Chain, and then Prism, which is our awesome ETH2 client, and a high-level overview of that. And so let's get started. With Prysmatic Labs, we are a team of 6. We are implementing a production quality ETH2 client in Go. There's Raul, Preston, and myself, and there's Nishan, Ivan, and Shay. And also shout out to 50 awesome contributors that also help us so much as well. I've also mentioned that we're hiring, so if you're interested in joining us, feel free to send us an email. So in the next few slides, I will briefly cover what ETH2 Bitcoin Chain is, and it's not as unknown as last year, because there's lots of great materials out there. There's also education series out there, but I will still briefly cover it so people can get a solid understanding. So Bitcoin Chain essentially sits between the ETH1 chain and then the shard chains. It acts as an anchor, as a spine for those both chains. And it serves as a playground for validators, right? So it's not for users. There's no user transactions there. There's no dApps there. It's only for validators. And why use Anchor? It's because it's important because the shard chains will use Bitcoin Chain as for cross-shard communications, and that's the only way for shard chain to basically pass that message to each other with certain security guarantees. And then in the future, the ETH1 chain will also use the Bitcoin chain to lower insurance, such as the penalty gadget. And it's really important. It's really important we do a good job here, because this is where the money is, essentially, right? So to go into a little bit more details on the Bitcoin chain, I did mention the Bitcoin chain is where the validators are. And to become a validator, you essentially send a one-way deposit via deposit contract, and that's on the ETH1 chain. And then in the current spec, it's 32 ETH to join. And then if your balance fall below 18 ETH, and your validator will be kicked out. But as a validator, you can also voluntarily exit. And Bitcoin Chain has certain nice properties, such as shuffling and randomness. So currently, we use Randall for randomness. And Randall is unpredictable, unstoppable. It has great liveness, but it's biasable, which is known as the validator's dilemma. That's why a group is also working on VDF, which should be launched in the next few years. And Bitcoin Chain also handles rewards and penalties for the validators. The rewards and penalties are calculated at the end of the epoch. And if a Bitcoin Chain doesn't give penalty, which is this nice property, which I will cover later, and then the validators will be punished for, and such that's called inactivity penalties. And then Bitcoin Chain is proof of stake, so you utilize proof of stake for the finalization, which is known as Casper FFG, and that you can basically build a nice penalty gadget for like ETH1. So it's very important. So just like every other blockchain out there, right? A Bitcoin chain is without a chain. It's not a chain unless there's block, right? And then when there's block, there's also state. So here are the two high-level structures out there. So if you look at block, it's very similar to like to the ETH1 block out there. You have your slot number, you have your parent root, which you can link back to the parent, and then you have your post-state root, which is what happens to the state root after you process the block. You have the signatures to make sure that block is coming from the right proposers, and then you have a bunch of different fields in the body. So I will get into more what those fields are later. And then you have your beacon state. So your beacon state essentially covers what happens after you propose the block. And then note that not every field in the beacon state changes after you process the block, right? The beacon state is designed in a way for efficient hashing and caching. So only a certain field gets updated on per slot level, and most of the fields gets updated on per epoch level, and this is just to avoid expensive hashing. So let's look at beacon block processing, and you can think of this like a pure state transition function. You input a block into a state, and then you mutate the state. The state changes. So when you input the beacon block into the state, you first have to verify that the block is correct, the block is valid. So you verify the slot, you verify the parent root, you verify the signature, and then you start mutating the certain fields in the state. You start mutating the Randolph field for the randomness, and then the ETH1 chain data field, which is to reference back to the ETH1 chain, and then you start processing each body within the beacon block, such as the transfer, exit, deposit, attestations, and that's how you essentially process a beacon block. And then that's how you process a beacon block, and this is how you process an epoch, right? So basically, there's 32 slots in an epoch. So after 32 slots, which is 6 minutes, you process the epoch, and then you essentially update the state by itself. So you look at the state, you see whether I can justify the state, whether I can finalize the state, and then you update validators balance within the state, and then you process registry update, which means that you activate, you add new validators, and then you make sure whether there's any slashing that had happened in the previous epoch. And if there's slashing, then you slash the validators, you keep the validator out, and so on. So now let's talk about what a validator has to do. So at the minimum, the validators has three duties to perform in the latest spec. And the only role that it has to do, or that it must do, is being an attester. So as an attester, you vote for a valid block, which is or you can say head at this point, right? And then you essentially vote for the head block that's used for choice, and then you vote for the epoch boundary block, which is the first block of the epoch, and that's for the finality gadget, which I will get more into later. And then for the phase one, you will of course vote for the shard data as well, but it's coming in phase one. And so you, as a validator, you are always one attester per epoch. You may or may not be a proposer. Let's say if you're a proposer and you're lucky enough to be a proposer, you're supposed to build a block on top of the parent block. So you essentially extend the beacon blockchain. And then by doing so you contribute to randomness via Randall, and then you also help to build the reference points to the ETH1 chain. And then most importantly, you have to collect and you pass the beacon chain operation into the beacon block. That's how attestations, deposit, exit request gets on chain. So yeah. And in the latest spec, to avoid spamming too many attestations in the same gossip pub channel, a new role was introduced, and this new role is aggregator. So aggregator essentially aggregates the attestations via the BOS signature scheme, and then you broadcast the aggregated version of the attestation. So right now there's about 16 aggregators per slot and per committee, and then you the aggregator broadcasts and then via different subnet. So as a proposer, when I package the attestations in the blog, I don't necessarily listen to every attestations, right? Because that's gonna get too spammy. So I will listen to the attestations that's coming from the aggregator. So it's all about crypto economic at the end of the day, right? So how does a blockchain sustain itself with great security? Everyone has to be incentivized to do their job correctly, right? That's why there's reward and there's penalties. So being a proposer, you get rewarded by including attestations, transfer, and all these objects onto the chain. And then the more rewards you get by including attestations faster, the more rewards you get by doing a better job on that, right? And then as a tester, how do you get rewarded? You get rewarded by voting on the correct head block, and then you get rewarded by voting on the correct FFG block as well. And then in the phase one, you also get rewarded by including the right phase one, which is the shard data. So aside from processing a block, a node also needs its own independent for choice, right? So you may ask, why does it need for choice? Why can't every node just accept the latest block as head, right? Because different validators can produce and receive blocks at different times. So how do nodes come into consensus on what is a canonical chain, right? And in Bitcoin, which uses proof of work security, it's easy. You always follow the longest chain because you know the longest chain has the most work, right? But in ETH2, with proof of stake security, instead of following the longest chain, you follow the chain that has the most validated votes, right? So the for choice essentially helps you filter out to a canonical chain that has the most validated votes. So this is a for choice that's used for ETH2. That's the LMD goes for choice rule. So it tracks validators' latest vote, and then you start at the head of the chain. And then when you face a decision, you don't know which branch to go to. You follow the branch with the most vote. So so if you look at the blue square, and each blue square represents each one vote of a validator. So and then you start with 5, you go to 5, you go to 5, and then you have decision to make whether you want to go to the top block or go to the bottom block. And so in this case, I'm going to the bottom block because the bottom block has 3 votes, right? And LMD Ghost for choice has this really nice property. It allows parallel processing. So if you look at the bottom branch, there's 3 blocks, but those 3 blocks are not building on top of each other, but they all still justify the same parent. So that's what's one nice property about LMD Ghost for choice. And there's different client implementation of LMD Ghost for choice. Previously, we used the naive spec implementation, and it was a little slow for the amount of validators we have on our testnet, which is currently like 30,000 testnet. And then we switched to a proto array for choice. Shout out to Proto Lambda for coming up with that. And then that implementation was just a lot faster. So the for choice gets calculated on per slot level, and it gives you the head, but versus the finality is calculated on per epoch level. So it points and updates you to the latest finalized checkpoint, right? So in ETH2, Bitcoin Chain uses this finality gadgets, which leverages a property called finality. So once a block is finalized, it's always going to be in the canonical chain, right? Unless there is a finality reversion. And finality reversion is really bad, right? Because meaning that there's 2 conflict finalized block, which this means that 1/3 of validators double vote, and then that will just burn more than 1/3 of ETH stake, right? So this awesome use case could be leveraged, for example, finalizing the ETH1 block. Also, like you will help syncing a client really well. So instead of syncing from the genesis, you can just sync from the latest finalized checkpoint. So that was a high-level view of ETH2 client. Sorry, that was a high-level view of the beacon chain. So I'm gonna shift gears and talk and do a little dive on Prism, which is our ETH2 client. So when we say ETH2 client, it generally consists of two main components. There's the beacon node and there's validator client. So the beacon node maintains the state of the beacon chain. It communicates with other beacon nodes via P2P, and then it responds to validator client requests. A validator client is relatively lightweight. It maintains the private sensible data, which is example the private keys, and then you query beacon nodes and perform duties such as testing, proposing, aggregating, and you can this paradigm doesn't really change much for phase one. For the phase one, it just means that we're include shard data, and then for phase two, it means that we're basically go beyond the data storage functionality. We're bringing state execution. So what's inside the beacon node, right? And inside the beacon node, there's multiple services. You can think of each service as its own thread, and it does one job. It does one job really well. For example, for you look at sync service, its job is to gossip and receive blocks from other peers. You can think about for choice service, and its job is just to run for choice and to provide head to the other service. And then state transition service, its own job is to process block, process attestations. And then, of course, the beacon node has its DB, you have its own cache, and then you utilize a bunch of third-party package as well. And then now there's the validator, right? And then what's inside a validator? And then the validator it handles key management, and that's important because it handles private keys for signings, and then it does multiple things. For example, proposing a block, attesting a block, aggregating attestations. Depends on what the validator is supposed to do at that given epoch, and it also has protections against slashing attributes. For example, it has this DB to disallow a validator to double propose or double attest, because that's a slashing condition. And props to Ivan for doing most of the work on the DB side. And then there's we definitely use a lot of third-party packages on that as well. So it's important to standardize the RPC interface between the beacon node and the validator, because it's important to come to standardization. So like people know like what they're talking about, right? So we have basically we have essentially researched like what's the best technology to use for standardizing this type of API. So essentially, we want to have a central repo to reduce disparities between services across different ecosystems. So we are using gRPC for beacon chain validators communications, and then it also supports JSON over HTTPs as well, so which is really nice. And then I would highly recommend everyone to check out our Swagger page. Most of the APIs are defined, ready, and functional there. And this is where we really value the community feedback. So we have gotten so many great feedback from different members in the communities. For example, what they want to see, right? They want to see blocks, they want to see attestations, like what's the best way to query those informations. And then there's actually 2 block explorers building on top of this API. So shout out to Etherscan and Bitfly. And Preston will do a demo on them later, but they all use this API. So if you want to build like cool stuff wallet software, block explorers, anything, please check out this API. And we're a huge proponent of using open source libraries, open source softwares. And here are a couple of core components that we're using. So we use FlowDB, we use DP2P, we use RPC, and then we use Prometheus and Grafana for matrix gatherings. And here's just a quick overview diagram on how to become a validator. So you essentially send 32 ETH to the deposit contract, and that's on the ETH1 side of things. And then the deposit contract is actually recently formally verified. So very excited about that progress as well. And the deposit contract will emit a deposit log, and then the beacon node will essentially monitor those logs. And then after a certain time, to ensure there's no forks in the ETH1 chain, and will create, and the new validators will get inducted in the beacon chain state, and that's when the new validator can start validating and testing. And here's some validator life cycles. I did mention the validator is really lightweight. Its role is to propose block and attestations. So validator will connect to a beacon node via RPC, and then you will wait for the chain start allowed, and then you will essentially, on per epoch basis, you will check whether the validator is active. And once it's active, you'll start performing its role, whether it's proposing, whether it's attesting, and then do all the cool stuff. So yeah. And that was my last slide. So I'm gonna pass it over to Preston, which will explain more on the testnet side of things. So I'm gonna add it here.
Thanks a lot, Terence. We do have one question, if you want to answer it, is how do you avoid validator collusion?
Well, so I think it's important to define what is collusion, right? So collusion could mean like a validator is lazy, for example, doesn't do their job, it just follow all the validators vote. And in this case, for phase one per se, that's where the data availability comes in, right? So there's proof of custody to ensure that every validator is actually downloading its own data, right? And then with proof of custody, you can actually whistleblower. You can basically call out other validators for not doing their job correctly. And then so there's definitely game theory there in play. But yeah, that's a great question.
Yeah, and another part of that is that it's hard to predict the future because of the random perspective of things. So when you're trying to collude with a certain set of validators a certain amount of time, you won't know the assignments except for a few minutes before, a few epochs before those assignments can be given out. So that makes it very hard to do these long-range collusions.
Yeah.
Okay. All right. So what I want to talk about here is how we're using and testing and running Prism in this testnet environment and preparing for a mainnet launch this year. So let's go ahead and dive right into it. We've been running testnets and experimenting with public infrastructure since May of last year. So it's been just over 6 months, 7 months that we've been working on this. And on January 9th of this year, we launched our most recent and currently active testnet with 16,000 validators, which is the full mainnet configuration. So what we mean by mainnet is that previously we were running smaller, more faster testnets so that we could see things. We could test with a smaller set of computational requirements. So instead of running 16,000 validators, we only had to run 64, which is much more manageable when you're not really sure what's going to happen. So that's been a really big achievement for us. Some of the new features for that are that we're on the 0.9.3 version of the beacon chain specification, which is almost the latest one. The latest one is 0.10, which includes new changes for the BLS cryptography standardization. So we'll be updating our BLS cryptography library soon, and then we'll be on the final version of the spec that's going to production. As I said before, we graduated from a minimal configuration with a very small sample set of validators. We started with 64, scaled it to about 1,000, and that was really difficult to do. So when we tried to do 16,000, we thought it felt like it would be impossible, but our friends at Lighthouse had been doing it, so we felt confident, that it was possible and that we could pull it off. And after some few weeks of very hard work, we were able to do that. And today we're running with 35,000 active validators in the beacon chain, which is to date the largest ETH 2 testnet that's being publicly advertised. So that's a pretty cool achievement. The only caveat to this is that instead of using 32 ETH, which is the mainnet requirement for depositing to be a validator, we're only requiring that you have 1/10 of that, and this is all, of course, on the Goerli testnet. So this 3.2 Ether has no value, but it's a lot easier to manage and a lot easier to distribute than 32 ETH. Even though it's has no value, it's still easier. Besides that, everything is exactly the same. So all the time parameters, part of the minimal configuration was that you could be activated very quickly within just a few epochs. Now it's something like a 4 to 6 hours delay for protection against ETH1 reorganization. So we want to make sure these deposits are we want to feel confident that they're going to be in the chain and not face a reorg event. So everything moves a little bit slower, but this has been extremely helpful for building out tooling, infrastructure, and kind of user education to show people how long things are going to expect to take. We also had a lot of bug fixes and a lot of optimizations to go from under 1,000 validators to running 16,000 was required a lot of optimizations. And in fact, just before we launched the testnet, Terence did a live demo running all 16,000 on his MacBook at a meetup in San Francisco. So that was super cool. All right, so what have we learned from running this testnet? It's obviously been a large part of our time and a lot of effort. It's been the majority of the work that we've been doing in the last year. Since the spec has been pretty stable, we've implemented all of the logic, and now we're just finding things that are really difficult to write unit tests for. So these edge cases and kind of unpredictable scenarios. So let's take a look at some of the things that we've really learned from running a test network. One of the most important things that we've realized is that having excellent metrics and monitoring is really helpful. Here we can see this is a screenshot of our old testnet where we were running only 543 validators, and you can see, there's some differences in balances here. Some validators are performing worse than others. So even at this stage, we're kind of wondering, what is going on, and how can we understand the performance of the network? And it's especially helpful when you want to validate your assumptions. So I had a theory that the increase in peers was contributing to additional load on the servers, which was then causing a higher rate of reorgs. So I was able to write these queries against our metrics and monitoring to assure myself that's not what was happening here. We can see a pretty consistent peer count and an inconsistent reorg count. So it must have been something else that was causing that issue. So this has been a really helpful tool. It's especially helpful when things are going horribly wrong. So in this screen, in the top left, we have the slot count for the various nodes that we're running and the justification, and you can see it goes from being a nice linear staircase here to a jumbled mess like earthquakes going off, and our CPU is going off the chart, memory usage is going crazy, reorgs are increasing to almost 100, Go routines, which are the number of parallel processes, are reaching 200,000. That's insane what's going on. Things are dying. So being able to visualize pain in the network has been extremely helpful. And all of this type of functionality comes with the Prism client. You can collect this data for your own node and be able to look at dashboards like this and understand how your node is performing, especially when you want to understand the performance of your validator. Another thing we really like is code instrumentation. So when we're looking for ways to improve the code, we think we can see something like block proposals are taking too long, or it feels like they're taking too long. So we can kind of dive in step by step and see where are the bottlenecks here. So in this example, we see a validator performing two operations. First, it's updating its assignments, and this takes 1.17 seconds, which is quite a long time, we think. And this has to do, a majority of the time is spent in processing in Epoch. So maybe there's something there we can investigate further. Likewise, with proposing a block, this should be pretty lightweight performance, pretty lightweight impact just to propose a block. But for some reason, it's taking nearly 300 milliseconds. Maybe we want to dive into that. It looks, we could see that some operations are fast, some are slow. Maybe it's going out the door on the peer-to-peer network. The only way to know is by profiling and having code instrumentation like this. So that's something that has been extremely helpful, especially in the early stages of the client when we had very little understanding of how things were performing at runtime. Diving into this example here, you can even see error messages. So this has been helpful for tracking failure requests. So in this example, we could not get our assignment for our validator for whatever reason, and this will help us understand what went wrong and how we can fix it. Another really helpful tool is using pprof and taking profiles of your running application and using what's called generating a flame graph, which is what we're looking at here. So what happens with this is part of the Golang tooling and infrastructure kit is that you can expose basically a debug port where it will start, once you query this this endpoint, it will start sampling all of the code that's executing at runtime and then generate a report based on that. So this is really helpful for when you're running locally and you can see your computer's getting hot or you're using a lot of memory and you want to understand right then what is happening. You could take a profile and see exactly what's going on. You can see the things in red that are very expensive. Of course, the bars that are larger represent a larger amount of time. So here we can see that updating the latest attestation because of executing a state transition is taking a long time. Also, marshaling the state to the database is taking a long time. So maybe we could find a way to make that a little faster. So this has been probably the most valuable tool we've had so far. Highly recommended if you're a Go developer and looking to find either micro optimizations, shaving off a few milliseconds here or there, or really understanding where are the big bottlenecks in your application. Another thing we do is we check in a lot of fixes to Prism. I haven't looked at the repository stats recently, but it feels like we're checking in 5 to 10 pull requests per day, even on the weekend. I think yesterday was especially productive for some reason. Maybe just a Saturday and we were feeling good, but we have a lot of changes flying in all the time, and we don't want to make things worse. So we practice what's called canary analysis. So when we have a new change to our master branch, we will create a new release candidate and then deploy the existing release candidate and the new release candidate side by side and shift some of our production traffic to both of these binaries and then compare certain metrics. So did the memory usage increase or the CPU usage increase? Did RPC methods start failing wildly for the new release candidate? And if so, let's block that release from going out into the testnet and kind of take a look at it. So this has saved us a couple times from killing the test network, and it's just been a pretty great resource for handling production deployments. As Terence mentioned, we put a lot of time into what we call this Ethereum's API, and it's intended to be a standard and common API for RPC server for Ethereum 2.0. It supports a protocol called gRPC as well as JSON over HTTP. So certain applications, like in a web application, it might make more sense to use JSON, or if you're using a more performant tooling or client, you would prefer to use gRPC. gRPC comes with a lot of added benefits, including generating your code stubs for you and a lot of other nice stuff. So it's super cool. This is what testnets are using to collect data from Prism and display it in a helpful way. So we can take a look at these two block explorers that have come up recently. The first one is Beacon Chain from Bitfly, and then we have the Beacon Chain Block Explorer from Etherscan. So let's go ahead and I'll show you guys what that looks like. Okay, so the first one here is the one from Bitfly, and we can see sort of the network history here, how many validators were activating. We had this green line, which was a long queue of validators, and then it's kind of leveled off here. There's not really anybody in the queue now, so pending validators is 0. That's great. This is all looking really good. You can take a look at, if you're running a validator in the Prism test network, you can take a look at your performance. So let's take a look at this guy. Oops. Well, maybe that one's not working. But anyway, this seems to be slightly out of date. But yeah, this is a really great resource to understand what's going on from Bitfly. And the other one we have is the Etherscan Beacon Chain Explorer for phase 0. It's been super helpful. It's very similar to the other one, but it also links with the Goerli testnet. So when you make your deposit to the deposit contract, you can see it here on Goerli. And let's open up the Beacon contract, right? So here, let's just take a look at this one. Someone's deposited 32 ETH to become a validator. And here you can see their validator public key and get a quick link into the performance. So they're actually waiting for inclusion. There's 6 validators in the queue according to Etherscan. So that's super neat. It's all kind of tied together. Etherscan's done a great job of representing Ethereum 2 data here. All right, back to the slides. Right, another thing that we have is the ETH2 stats portal. And what you can see here is a group of self-reported Prism nodes that have opted into this sort of data collection. So here you can see my validator with the gemstones there, and a couple of ones that Prysmatic Labs runs, and then a few other users from our testnet. In this portal, you can see that 37 nodes are reporting, self-reporting, but there are well over 37 nodes. So for example, this guy at the bottom there has 102 peers, which means that there must be at least 102 validators or beacon chain clients running in the testnet. So this is pretty cool. If you decide to participate and run a validator and kind of practice this in Prysmatic Labs testnet, be sure to sign up with the site, because it's pretty fun to see your name up there and see how you're doing relative to everybody else. It's pretty cool. Speaking of that, if you do want to participate, the website is prylabs.net, and this will help you get you started. So I'll go ahead and open that now. Here we have prylabs.net. This is the Sapphire testnet. To get started, you just need to click become a validator. The recommended route here. So if you want to try ETH2, this is the great place to do it. We recommend to use Docker. So you Docker pull down these images. That's a really easy way, a really fast way to get started. If you're a little more, technically inclined, and you're not afraid to compile from source, then we have additional documentation. Clicking here or read the docs, and that will sort of help you build from source, and you can kind of do without Docker if that's your preference. So the getting started on ETH2 is as easy as 6 steps here. First, we'll get Prism, so we either compile it from source or we use Docker pull, and then we'll need some test Ether to do our deposit. So you'll either need to install MetaMask or use Portis. Let's see if I have MetaMask on here. MetaMask not working. Let's try Portis. Okay, Portis is doing something. Just a moment, it's having me log in another window, so you might not see it. Logging in. Oops. I don't remember my password. Well, I can't remember my password for this, so my test ETH is gone. Oops, oh well. And MetaMask does not seem to be working. But let's imagine that I did that. Oh shoot, I can't click through. Anyway, if I had done that and I don't have any test Ether, this will open up a link to the testnet faucet. So we'll gladly give you a little bit of Ether. And of course, if you want a larger quantity, to want to run more than one validator, come join us in Discord and drop us a line and let us know, and we'll send you a few hundred to help you get started. So this will show you how to generate a public and private key for your validator. It will show you the instructions for starting your beacon chain server and running your validator client. And then it will help you send the validator deposit and give you some instructions and expectations of how long this is going to take. So part of the process, as I said before, takes a few hours for deposit inclusion. And then if there's a large queue of validators, you'll have to also wait your turn to be activated. Okay, back to slides. I just have a few more slides here, and then we'll have a few minutes for questions. Okay, so that's our test network. And what is left for launching ETH 2 this year? So the goal is to launch it this year. As I said before, we're on the ETH 2 specification of 9.0.3. The latest is 0.10, and 0.10 is the sort of the final breaking change that we can expect for phase 0. So that included the standardization of the BLS cryptography library. So once we get up to spec on that, we're going to start coordinating more aggressively with other client teams such as Lighthouse and Nimbus, Lodestar, and others to form what's called a multi-client testnet. Part of launching ETH 2 is that we have 2 or 3 or potentially more options to choose from when it comes to a beacon chain client and a validating client. So we have some sense of redundancy there. If there's a major bug in one of the clients, well, it ideally doesn't affect the majority of the network. We hopefully have a pretty even distribution between the validating client options. So that sense of redundancy is going to be really helpful. And having a multi-client testnet is the next step towards weeding out the final bugs. We last year had a very successful interop experience. So we tested out what is the interoperability in the current state of our clients, and we were able to get a short-lived test network of I think 7 or 8, maybe 8 different client implementations all at the same time. We were all in the same room on the same network, so that worked out really well. But it doesn't simulate the real-world experience of the chaos of the internet. So that's coming soon. We're very close, and ETH 2 will be coming this year, so that's very exciting. And that's the end of my slides. So we can take questions now. Let me switch back over. Okay, close video. Okay, I'm catching up on the chat here. Terence, have you been following with the questions?
Yeah. So first question, after ETH is open, will the price be equal to ETH?
After ETH 2 is,
will the price be equal to ETH?
Yeah, that's a good question. So I'll give my answer, and then Terence, if you have a different one, you can give it too. So the migration path for ETH 1 to ETH 2 is a one-way transition, meaning that once you migrate your ETH over to ETH 2, it's part of ETH 2 and is no longer part of ETH 1, so you can't take your rewards back at the protocol level. So will that be trading differently or at a premium or at a discount? It's kind of hard to say, but that does bring in an interesting secondary market, because people may want to still transfer back to ETH 1, and you'll have to do that through some, I don't know, layer 2 or OTC or someone who's willing to make those kind of trades.
Right, and one of the important initiatives that's being worked on by the ETH1.x group is to enable this two-way bridge, whether you can transfer ETH back from ETH 2 to the ETH 1. So with that enabled, probably sometime in phase 1, that the price will definitely be a lot closer. But initially, I would think there will be like arbitrage opportunities from the exchanges. So even then, the price should be pretty similar with that. Okay, second question. There's Cosmo folks. They're working on Game of Stakes for the testnet. Is there anything similar to Game of Stake for the ETH2, or is it too early?
We were talking about it, right? I don't know what the latest was. Do you recall?
I don't neither. There's definitely discussion about it, and I mean, we probably have to get to multi-client testnet first, and this will be more like a second iteration, third iteration of the multi-client testnet, I think.
Yeah, that's definitely when it will be most beneficial. It's probably not worthwhile to do for a single client testnet like Prism. But when we have this sort of like final long-lasting multi-client testnet, that's kind of when it makes sense.
Right. And then there's a question on, so it might be risky to stake Burma ETH for getting ETH2 back. What do you think?
Might be risky to stake your ETH. There is always a little risk with these kind of technologies. But with this risk, there's also reward. So you're earning interest for your participation as a staker. And if you're early, the interest is higher than if you come a little bit later. So there's a risk-reward trade-off.
Right. So it's important to get the economic parameters right so that we get the right amount of people to stake in the beginning, given that risk. And then that's definitely one thing we need to formalize. And people are working on that right now.
Yep.
And let's see.
So another question is, how will exchanges such as Coinbase handle I guess the transition from ETH1 to ETH2? That's a good question. I don't know. Do you know, Terence?
I don't know. Yeah. Coinbase about it.
Are they here? Are they part of this conference? That might be a good question for them.
Yeah. Anyway, okay. Next question. What would the validator registration look like on mainnet? We'll definitely want it to be as easy as possible. That's something that my mom can do it. And that's where we do value feedback from the users today. So Preston, they present their 6 steps to essentially send a deposit and launch your validator client to the testnet. And then ideally, the less steps, the better. But we also have to think about the securities point of view because of it is real money. So you don't want to lose 32 ETH. So it's definitely, I would say it's a work in progress.
Yeah. Mm-hmm. Yeah, so the registration process will look pretty similar to what we have today, but be a bit safer to prevent you making mistakes. As we know that cryptocurrencies can be very unforgiving. So we want to ensure that it's a good experience for everybody. That starts with a clean UI and a good understanding or education of what's happening. So not only telling you what to do, but why you're doing it and giving you that control of what's going on. So it would be that you first want to sync your beacon chain, and then you want to make your deposit, and then you want to have some monitoring in place so you're understanding how the performance is going on. So there might be some like alerting through the application itself, or just some diligent checking on it every once in a while.
Right. Let's see.
Says okay. Another question is: there will always be ETH1 left, zombie accounts, etc. Will ETH1 be closed down practically since there will be no dev work on ETH1? So, I guess like thinking about the migration here, we have this. Imagining we only have a one-way bridge, just ignoring the idea that we could have a two-way bridge. Once we've transitioned fully with phase 2, so everything's ready with phase 2, we can imagine a migration where we stop the bridge between ETH 1 and 2 and initiate a new shard with the data from ETH 1. So basically carrying over all those accounts that didn't opt in early, and then the Ethereum Ice Age, which is the increasing difficulty bomb, will kick in, and ETH 1 will sort of grind to a halt eventually.
Right. So as a developer, I would imagine it should be a very seamless process. Like you would essentially have to restore your node. It's just similar to a hard fork. You have to restore your node and then point to the right test network, or like in this case the mainnet network. And then next question: when will proof of work mining fully begun from Ethereum?
I guess it's a bit of a tricky question, because the proof of work mining as we know it today would go away when we fully migrated to ETH 2 and no one mines on the ETH 1 chain anymore. But there's also the what is that thing, the randomness thing called?
Random?
No, not the other one. The verifiable delay function, which is a type of proof of work. So it's a little bit tricky. We'll still be doing some like computational stuff, but it won't be in the same manner.
Nice.
And I don't think I made any miners angry, because there are still alternatives. And if they're holding on to a large part of their ETH rewards, then they could be staking, which is a lot more efficient in terms of energy.
Yeah. So, Preston, what do you think is the competitive advantage of your client versus others? This is a good one. And I can go first. So personally, I think the Go language is really like easier to learn versus like Rust. So personally, I joined Prysmatic Lab 2 years ago, and I didn't know any bit of Go, but I was able to jump into it, spend a week reading a book, and then just dive into it. So I'm a fan of the Go language. I think that's one of our main strengths.
Yeah, so we kind of wanted to play off of the success of Go Ethereum. In fact, we wanted to build Prism as an extension of Go Ethereum. Because we really liked it. We really liked the way it works. We liked that we could understand Go very quickly without having to, not being a Go expert. Some of us were not Go experts at the time, and I think you never are fully a Go expert. You're always practicing and getting better, but it was easy to get into very quickly. So we really liked that part of it. So we think that's a competitive advantage for other developers. If the code is easy to read and understand, it'll be easier to trust it and find bugs and stuff.
Okay. Last question.
So last question. So the time we have for it's asking, is day one going to be 100% proof of stake full migration, or is the migration happening in phases? That's a great question. I can start with that. Is that the phase 0 is launched with 16,000 validators, and it is launched running alongside the ETH1 chain. And then we move on to other phases. Of phase 1 is bringing in the shards and the data layer, and then phase 2, which is the execution environment. So it is a gradual migration. It's not all at once, but it will be, the beacon chain at least will be 100% proof of stake on day 1, but we'll be running both of them in parallel for a little while.
All righty. Well, thank you, Terence and Preston. Really appreciate your time. And we got to move on to the next panel or workshop. So thanks again, and stay tuned because the next one is going to be super interesting. Thanks again. See ya.
Bye.
Bye.